Como
mediciones que hay que dejar cargar. Gracias por utilizar la pregunta puede ser.
Ya estamos. Es bueno.
bien, he probado lo del puntero para ver qué.
Porque de verdad que algo tiene.
Sí, lo único pero
no pueden decir no te lo preguntas.
Vale, ya estamos retransmitiendo, luego lo edito.
Sí.
¿Se ve por el Zoom ya?
Se ve por el Zoom y se ve en YouTube. Ya, está bien metido. Entonces esto yo creo que lo puedo actualizar. Esto es lo que tenemos aquí retransmitiendo, está cogiendo el sonido bien de aquí. Y seguramente si alguien hace una pregunta por Zoom, te va a salir por ahí, lo cual se debe oír bastante bien.
El sonido.
Sí.
Ok. Vale.
Todo se puede complicar más. Está bastante complicado esto. Y ahora pinchamos aquí, porque si no, el ratón no te va a avanzar.
Mira, a ver, control esto del...
Yo me voy a conectar a YouTube. Y ya sabes, si te vas muy para allá, no se te va a oír. Lo mejor que te quedes instalado.
No me voy a quedar sentado. Mira, es puntero.
Sí,
como los del tribunal están
contamina menos.
No tengo. No veo. Se me ha liado. Sí.
¿Y se puede seguir online?
Sí, yo voy a pero no me voy.
Ah, vale.
Por eso.
Sí.
Es para la primera. Oigan, el resto tengo que cambiar. Bueno, algunas cosas. De hecho, ¿sí? Vale.
Bueno, espero.
Listo. Entonces,
Te ve, tienes que estar aquí. Si te metes más para acá, se te corta.
Tampoco te quiero.
Tienes que estar aquí. Si pones más para acá, ya te corta la cámara. Esperamos siempre un poquito, ¿no? Para si se conecta.
Sí, un par de minutos.
¿Siempre es en inglés o hay veces que se ha hecho en español?
Yo presento en español. Yo te voy a presentar en español.
Yo lo voy a dar en inglés por...
¿Tú lo vas a dar en inglés?
Sí. Por uso.
Sí, normalmente es en inglés.
Seguramente todo en inglés.
La presentación también la
Sí, porque es una conexión internacional. Sí, porque además tampoco sé quién se lo conectará. Se lo he dicho a gente de fuera que no hablan español. Vale, que yo creo que es mejor en inglés, por si acaso.
De cara a la defensa. De cara a la defensa.
Sí, también, la defensa. Pero que como se lo he dicho a gente de la comunidad de estrellas masivas, que son de fuera, entonces...
Sí.
¿Están conectando ya o...?
Sí. Yo creo que un minutillo más y...
Yo no sé si a lo mejor tú tienes que estar en monte y tienes que hablar ahí, porque si no se va a acoplar.
Representa David.
Vale.
Yo lo que
Entonces,
luego para las preguntas, si eso ya cambia.
Ya está muteado.
Bueno, pues vamos a empezar entonces. Bienvenidos a todos a un seminario de Astrofísica de IPARCOS de hoy y tenemos el gusto de tener con nosotros a Abel de Burgos Sierra, que se formó aquí en nuestra facultad, hizo su grado en físicas aquí terminando en 2016, continuó haciendo el máster entre 2016 y 2018, al tiempo que también estaba trabajando en Sept para el proyecto César y hizo además un TCM también relacionado con astrofísica estelar con nosotros. Y después, mientras estaba buscando para hacer la tesis, estuvo trabajando durante un año como operador en el Isaac Newton Telescope, el INT, y otro año también en el NORD, el telescopio nórdico en La Palma. Finalmente consiguió financiación para hacer la tesis en el Instituto de Astrofísica de Canarias, donde ha estado haciendo la tesis en estrellas masivas, que es lo que nos va a contar hoy, los últimos avances para entender este tipo de estrellas. Y además va a presentar ya su tesis justamente esta semana, me ha dicho, y además tiene ya preparado el postdoc para irse a Chile, para trabajar allí con una beca de la ESO en los telescopios VLT. Así que os dejo con él, que os va a contar todo este campo de las estrellas masivas en el que él está trabajando.
Muchas gracias, bueno, decir simplemente, me hace mucha ilusión poder estar aquí hoy después de tantos años de haberme formado aquí, tanto en el grado como en el máster, y un placer estar de vuelta con todos vosotros que al final me habéis formado. Así que gracias, y también gracias, David, por invitarme a dar este seminario. Lo voy a dar en inglés, por si hay alguien conectado desde fuera que no es nativo. So I'm switching to English. So the presentation that I'm gonna give today, it's gonna summarize some of the key results of my PhD thesis that goes into getting a better understanding or getting new evolutionary clues to understand the nature of massive stars. So I'm gonna give a bit of background about the star evolution, but first I'm gonna introduce what massive stars are. So massive stars are, at a glance, stars that are that are born with 8 or more solar masses. They are hot objects. They are very luminous, and across their evolution, they can reach very large radii. They are also short-living objects, especially compared to their less massive counterparts. And they are very important not only for understanding stellar evolution or massive star evolution. They have an important implication in other fields in astrophysics. They are traces of star-forming regions. They have an important feedback into the interstellar medium. They play a key role in the chemodynamical evolution of the galaxies. They have been also proven to be useful extragalactic tools. They play the main role in the reionization of the universe, and now we also know that they are the progenitors of the gravitational wave emissions. So for these reasons and many more, studying massive stars is very important, or getting the proper knowledge of the evolution of massive stars is key. So the talk that I'm going to give today, it's going to be focused in the study of B-type supergiant, this intermediate evolutionary state of massive stars. These Hertzsprung-Russell diagrams, I have taken them from the notebooks. This is what typically it's taught to the students, that massive stars are born, or most of them are born as O-type stars, in which phase where they spend most of their evolution. They are in the main sequence, but as soon as these stars leave the main sequence, they evolve quickly through the Hertzsprung-Russell diagram into to become later or cooler stars. In between is where B-type supergiants should be located, but because of this gap, we wouldn't expect Hertzsprung gap. We wouldn't expect to find many of these objects, right? So the reality is much different. This is called the TAMS problem. It turned out that even in the 1990, the work by Fitzpatrick and Garmany in the LMC, the Large Magellanic Cloud, doing a photometric study of the upper part of the Hertzsprung diagram, they found a large overdensity of B-type supergiants located beyond the theoretical end of the main sequence. And it wasn't just a few stars, it was actually a very large population of these B-type supergiants located beyond. Later on, in the work by Castro et al. 2014, in which the quality of the data improved with respect to the one by Fitzpatrick and Harmony, show a similar evidence that above a given mass, basically for those O-type descendants, it was quite difficult to really understand where end of the main sequence is, the terminal age main sequence. We can see here that above this point, it's rather difficult to find where it is the TAMS. By the way, I'm going to show several times this diagram. This is not a Hertzsprung-Russell diagram. It's a spectroscopic Hertzsprung-Russell diagram in which we use the spectroscopic luminosity, defined as 10 to the 4 divided by the gravity, as a proxy of the actual luminosity. Still, the problem, we can see this problem in the spectroscopic H-ray. Now, this has been a problem that has been on the table for more than 30 years, and still we have not been able to solve it. Now, if we assume that all the stars that we see follow single evolution scheme, like the one we would, or the one that would, that I'm showing here, then one possible solution would be to adjust to fine-tune the input parameters of the evolutionary models so that we can play with the width of the main sequence, and for instance, we could place it somewhere here. There are many internal parameters in the evolutionary models that can change the width of the main sequence, like the initial rotation of the stars, the efficiency and the type of angular momentum transport, mixing processes, the core overshooting, inflation, and mass loss. And I have put here an example from Martinez et al. 2021, in which playing with different evolutionary models, like those in which stars are born without rotation, or 0.4 times the critical rotation, plus different values of the core overshooting, we can get different widths for this main sequence. So, fine-tuning the models, we can try to reproduce what we observe. However, if B-type supergiants have followed different evolutionary paths, then the situation becomes more complex. In this regard, we could have not only stars evolving within the main sequence, but we can also have stars that are evolving bluewards from the red supergiant phase, for example, or even avoiding the red supergiant phase, evolving bluewards. Additionally, it is known now in the field of massive stars that many of massive stars are born in binary systems, and actually it is theoretically predicted that practically half of the systems that we observe as a single star actually interacted with a companion along their evolution. And this interaction caused significant changes in the evolutionary paths of these stars, which means that this region here may be populated by stars that have merged, for example, or that they have transferred, or that they have received matter from a companion. So the situation is quite complicated. Now, one of the things that I focused in my thesis was to locate the end of the main sequence. Now, in order to do this, the simplest way to do this would be to try to find the position in the HR diagram where we stop seeing, or we see a significant decrease in the number of objects. Because after the core hydrogen exhaustion and ignition of the helium burning, the stars evolve rapidly because of the expansion of the outer layers of the stars, what we traditionally call the Hertzsprung-Russell. So, as I was saying, one way to determine the end of the main sequence would be to find this drop in the relative number. I didn't mention yet, but I'm going to do it now. The work by Castro 2014 has several issues, and this is the state of the art until the work that I performed in the thesis. But the work by Castro had several issues. One of them is that this sample is inhomogeneous in the sense that it gathers data or spectroscopic parameters from different studies, each of them collecting different data from different observatories with different reduction and analysis techniques. And most importantly, they also didn't have distances, so they couldn't turn this into the classical HR diagrams. Another way to locate the end of the main sequence, another way that has been proposed, is by finding a drop in the projected rotational velocities. I'm showing an example here from the work by Vink et al. 2010, where we can see the projected rotational velocity, or BSGs, against the effective temperature, and how beyond a given temperature, there's a sudden drop in the BSG values. So, according to Vink, as also other authors, the stars that are beyond this empirical or adopted end of the main sequence would be stars that, as I said at the beginning, either they are binary products or they are stars that are returning from a cooler stage. So this would be one possibility, but also the same authors raise a second possibility for the drop in the BSG. It turns out that at this same temperature, theoretical models for mass loss in massive stars predict an important increase in the mass loss rates that can take enough angular momentum from the star, producing a spin down in the velocity. So here it's the rotational velocity. In red, we can see that it goes down at the time that the mass loss rate significantly increases. So we have two possibilities for the drop in the BSG. One would indicate the end of the main sequence. The other one is simply the consequence of the enhanced mass loss. Now, several studies, I put just one example here, but there are others that were using a relatively small sample of stars, were already seeing that these predictions by Vink et al. Were actually not so realistic, in a sense that if you divide the actual mass loss rates and you divide it by the predicted ones, we see that it doesn't really match. So this would indicate that probably this is not the case. But as I was saying, the number of stars was relatively low. There's a third way that we can use to locate the end of the main sequence for massive stars that has been proposed, and is by finding a lag in the binary detection. So when massive stars interact, in principle, this should occur within the main sequence, because then later on, once they reach this red supergiant phase, the chances to find a binary system are very low. Typically, I mean, the envelope of the red supergiant is so large that typically either, let's say, merge with the secondary component, or actually, if it explodes, a supernova, it can kick out the companion. So the chances to observe binary objects beyond the main sequence is quite low. Therefore, this would be like an indirect way to detect or to establish the end of the main sequence. However, in the work by McEvoy 2015, in which they analyzed B-type supergiants, again, the number of stars was relatively low, and therefore they couldn't make a strong empirical constraint to the evolution models for the drop or the lack of binaries. And here is when it comes the project of my thesis, in which I am investigating the evolutionary nature of these B-type supergiants by using a statistically significant volume-limited sample. So with a statistically significant volume-limited sample, we can address these questions in a proper way. We we increase the sample size with respect to previous studies, as I'm going to show you in a moment. We significantly reduce observational biases within the sample. We also perform an homogeneous analysis, not like in the work, for example, by Castro 2014. We also benefit from the Gaia distances at the test photometry. I will come to this at the end of the talk. And we can attempt to locate the end of the main sequence, find a solution to the drop of fast-rotating stars, use multi-epoch data, because for this sample that I'm going to introduce now, I don't have just one observation for each of these stars. Typically, we have 4 or 5 or 3 to 5 spectra, so we can aim at detecting the binaries. And at the end, I'm combining all the valuable information to find new clues on the nature of these B-type supergiants. So, beginning with the sample, I'm going to briefly introduce the sample that I'm using. It's a spectroscopic sample, so what I have are spectra that were collected within the Jacob project. They are part of the Jacob spectroscopic database, whose PI is my supervisor, Sergio Simón Díaz from the ISC. And and this spectroscopic database basically gathered spectra from three different facilities: the Nordic Optical Telescope and the Mercator Telescope in La Palma, and then also the NDE ISO 2.2 meters telescope in La Silla. So at the beginning of the thesis, this Jacob spectroscopic database had around 8,000 spectra, of which around 400 objects were B-type supergiants. Then during the thesis, I did a lot of observations to try to increase the sample size and the completeness. And by 2023, where I decided to stop collecting data, we gathered around 16,000 spectra of more than 2,000 galactic OB and A type stars. All of these spectra, by the way, are high resolution. We presented also this sample in a first publication. The location of the O-type stars as well as the B-type supergiants is shown here in this radial plot. Here would be our solar neighborhood or our sun, ourselves. We collected, as I was saying, total of, in total we observed 550 O-type stars and around 900 B-type supergiants. But now the key question is how many of those did we successfully analyze with our methodology? Well, during my PhD thesis, I ended up analyzing around 100 O9 type stars and more than 650 B-type supergiants. And in this sample, I am excluding BE type stars, so stars that have a disk around them, double line spectroscopic binaries, so systems in which you can see the two components of or each of the components of the binary system in the spectra, hypergiants, and some other problematic cases. Now, as I mentioned before, one of the things we wanted to ensure is that we reach a statistically significant volume-limited sample. But statistically significant respect to what? So we use the ALMA Luminous Star Catalog by Pantaleon y González in preparation. That is our best collection of, or database of massive stars, OB massive stars in the Milky Way. And we use this catalog to evaluate our completeness. We were very happy to see that basically for all sky targets brighter than magnitude 11, that can easily reach 3-4 kiloparsecs, we are around 70% complete. So this is enough to undertake all these studies in which we evaluate the end of the density. So, said this, I'm going to briefly introduce the methodology that I have used in order to determine the spectroscopic parameters of my sample. We call the analysis technique quantitative spectroscopic analysis, and basically it's divided into two parts. One in which we derive the line broadening analysis, typically the equivalent widths, the full widths, the projected rotational velocity, and the microturbulent velocity that is related to some motions in the atmosphere of the star. For this, we use two tools. One that I developed, which name is Jacob, and another one that is developed by Sergio Simón Díaz and Artem Guerrero, which name is Jacob Broad, that allows us to derive basically these two parameters. And then in a second part, or a second step, is the determination of the spectroscopic parameters and the abundances. So for this, we use fast-wing unclamped evolutionary models, and we introduce hydrogen, helium, and CNO and silicon model atoms. Then we apply a machine learning technique, a supervised machine learning technique developed by my other supervisor, Miquel Urbaneja, at the University of Innsbruck, that we call this program, typically call it MAUI, and it's an emulator of the fast-wing spectrum. Then, running an MCMC, we are able to derive the spectroscopic parameters, namely the effective temperature, the surface gravity, the wind strength parameter that I will describe later, microturbulence, and then the abundances that were introduced in the input models. We also did the detection of spectroscopic binaries. As I mentioned, we have on average around 5 spectra for each of the stars. And what we can do is to identify the single line spectroscopic binaries, so binaries in which you only see like one star and the spectra is moving to one side or the other because it has a companion, but we don't see the companion, either because it's a compact object, like a black hole, or because it's too faint to be observed. So, by measuring the radial velocity peak-to-peak amplitudes, we can see here, for example, two radial velocity curves in which these are individual radial velocities, one for each spectra. And we can see that in some cases, we see the spectra, or the spectrum, shifting from 100 kilometers per second down to minus 50 kilometers per second. So we define some radial velocity peak-to-peak thresholds that are changing with the spectroscopic luminosity and effective temperature to basically separate what is produced by variability. So all these stars have a strong variability, so the luminosity changes significantly. But this could also affect the spectral lines. So something that we may see as a displacement of the spectral line, it could be actually produced by variability. So we have some thresholds to say, okay, this change is large enough so that we do think this is a spectroscopic binary, and some other cases in which not. So we are able, through this way, to detect the single-line spectroscopic binaries. And then we have a set of diagnostic lines, namely helium-1 5875 and then the silicon triplet, to look for companions. I have some examples here, and you can see that in two different spectra, the position of the lines swap. So this is basically the two systems. And through this method, we are able to detect double or multiple lines. Sometimes we have SB3 systems. Additionally, within the methodology, we use the distances. We use the Gaia distances from Bailey-Jones 2021, corrected from 0 point offset. And then we also, for the photometric variability that we use to study the variability of the stars and the pulsational properties, I will come again to this at the end of the talk. We developed a Python package guided by Dominic Boma and Simon Brusens. That with this package, we're able to go from the test light curves to the periodograms. So this is the methodology that I have used. And now I'm going to present the main results of this work. So as I mentioned at the beginning, one way to locate the end of the main sequence is by finding the drop in the relative number of stars, for which now we have this excellent volume-limited sample with 70% degree of completeness up to 3 kiloparsecs. So, just as an example, if we limit our sample to 1.5 kiloparsecs, this is how our HR diagram looks like. Now we have incorporated the distances, so we are able to see the actual HR diagram for massive stars above 12 solar masses. This is how it looks like. I have separated stars into fast rotating stars, those that are in cyan color, with VSNI above 100 kilometers per second, from those that rotate, let's say, normal, in the sense that it's below 100 kilometers per second. This is how it looks like, but if we increase the volume, if we go up to 2.5 kiloparsecs, we gather around 700 stars, and now the picture changes a bit. We can start to see that there's here like some overdensity, which is followed by a relatively low number of stars. If we increase even more the size, if we go to 4 kiloparsecs, we don't have that many. Here we lose a bit of completeness. We don't get that many more stars, but the picture looks quite similar. We have this overdensity of stars here that is followed by a lower density of them. Of course, we translate this into a more easy way to see the drop. So we were using histograms. So for each of these 3 panels, we have 3 columns, and then each row separates the stars into different luminosity beams. Now we can see that, well, in all of if we only focus in the middle column, that is the one that we have, let's say, the best ratio between number of stars and completeness. We can see that in all the histograms, we see a sudden drop here, 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 and it's not so clear here, but this is for a reason that I will reveal at the end of the talk. but still there's a bit of some drop. So this drop is what we use to define the end, our updated, adopted end of the main sequence. I have put it here on top of the plot by Castro 2014, so that you can see how different it. Or I will show you now. I think it's the next one. Yeah, how different it looks like when you have like a proper sample with enough completeness and not biased in any way. So this is the location of the TAMS that we find. And this has very important, well, it's not exactly the same position, it shifts a bit, like for the upper luminosities or higher luminosity, it drops at 25,000 Kelvin, and then as we go down in luminosity, it shifts a bit to 22,000 Kelvin. But this has very important implication because traditionally, classically, all B-type supergiants were not main sequence stars, they were helium-burning objects. Now we know that even up to or practically half of the B2 type stars would still be on the main sequence. You can see also here the some state-of-the-art evolutionary models and how still we find this difference between the theoretical end of the main sequence and the empirical end of the main sequence that we have adopted. So this is very important reason. However, keep in mind that, as I was mentioning at the beginning, this could be populated also by some contaminants, namely those binary objects or those stars evolving blue ones. I will come to this as well. Now, regarding the drop in projected rotational velocities, that is the other method that we could use to observe the drop of the end of the main sequence, with our sample, we indeed see this drop. Here you can see very clearly. These two boxes translate into these two histograms, in which I show the number of stars against the projected rotational velocity. And you can see that practically we don't have any fast rotating star beyond approximately 22,000. Now, does enhanced mass loss rate cause a drop in this scenario? So this is the next question we wanted to answer immediately, because this would tell us if we can use this drop to determine or to locate the end of the main sequence. These are the predictions that I was mentioning in the beginning. So the work by Bing et al. Was predicting this enhanced mass loss rate. This is the plot that I showed at the beginning. And in order to test this, we derive mass loss rates. So how did we do this? So from the analysis, or from the spectroscopic analysis, we can obtain information of the wind strength. Basically, this parameter, we obtain it from the H alpha profile. And this wind strength parameter is connected to the mass loss by this formula that we see here. This is the stellar radius that we can get if we use the distances from Gaia. We have the terminal velocities that we obtain from the literature that we get through UV spectra. So the only way to obtain this is from using UV spectra. And we have everything. We can basically extract the mass loss rates that we derive for around 120 B-type supergiants. We couldn't include more because the number of IUV spectra that we have, or the massive star community have, is not so large, so there were not that many terminal velocities derived for the stars within the sun. This is the location of the stars in the HR diagram. We see, like, again, we are splitting into three luminosity beams. But the important figure is this one, in which I am showing the mass loss rate against the effective temperature for the same stars. And in the background, I'm overplotting the predictions by Bing 2001. That, by the way, these predictions are basically implemented in the vast majority of the evolutionary models that everyone uses. The jump in mass loss rate is between 10 to 20, depending which prescription you incorporate in the evolutionary model, or which fine-tune. Well, let's say that depending on the implementation, this prescription can change from 10 to 20, or can increase in the mass loss rate by a factor of 10 to 20. But we can clearly see that, well, there's no certain evidence of an increased mass loss rate over the stability region. So this was also one of the main results of the thesis. So this means that then the drop in the BSNI, it may not be, I mean, it's likely not produced by this enhanced mass loss rate, and therefore could indicate that indeed at that temperature we reach the end of the main sequence. So do they match the drop in relative number with the drop in BSNI? So I'm showing you here one of the previous figures in which I'm indicating our empirical TAMS. And if you remember, I was indicating with these cyan dots the position of fast rotating stars. We can see that, okay, in the middle part of the panel, they kind of the figure, they kind of disappear when we reach the TAMS, but then for the higher luminosities, there's a lower number of fast rotating objects. Actually, there's only one here. But here we see a higher number beyond the terminal edge sequence. So we were like, okay, then what is happening here? So what I did is I'm investigating the possibility that stars cannot pass a certain limit in the rotational velocity. And basically what I was investigating was the critical velocity of these stars. Evolutionary models provide you the critical velocity for your models, and by using the average BSNI value for my fast rotating component of the sample, that is around 220 kilometers per second, I could see that basically where models predict that this critical velocity reaches that rotation is where I stop seeing the fast rotating objects. Which means that, okay, then we found an explanation for this lack of fast rotating object that was at the end simple explanation. Furthermore, I calculated the ratio between fast rotating objects, the ratio between the number of stars before the TAMS and after the TAMS, which is 4:1, as also within the main sequence, the ratio between all stars and only those fast rotating, which is 3:1. This provided me that I should observe or I should detect around 12 fast rotating objects after the TAMS, and of which I have around 8. So it was relatively simple. I mean, at the end, what we found is that the lack of fast rotating stars may be explained by the drop in the relative number as we cross the TAMS, plus stars reaching their critical velocity. You can see here also some scatter plots of the BSNI against the effective temperature, and this is, let's say, the limit imposed by the critical velocity. Also interesting, there are some stars, I don't know if you are able to see, that are marked with some crosses. These stars exhibit in the H alpha profile some signs of having a disk. And this is because once they reach the critical velocity, they expel this material that at the end they end up circulating the star. So everything matches or makes sense. We also investigated whether there's a lack or not of SV1 system or binary system beyond our empirical TAMS, which I show in this figure. So in this figure, I'm only showing stars up to 2.5 kiloparsecs, but limited to those cases in which we have at least 3 or more spectra. Otherwise, I would be biased. So here, I'm just showing those stars in which we were able to say whether we detect an SV1 system, single line spectroscopic binary, or not. And interestingly, we do find a drop in the number of SV1 systems from the main sequence to beyond the TAMS. It goes from around 40% to 50%. So there's indeed a drop of SV1 system that we can also use to say, okay, here's where it may happen at the end of the main sequence. Additionally, the percentage of SV1 system decreases within the main sequence from 44% to 34%. My personal point of view or reason for this is that at the beginning you have binary systems, but at some point the most massive star will evolve and either will merge with the secondary, or you will have well, mostly this one. Like you will have these systems in which sooner or later the primary will merge with the secondary, and then you would see a decrease in the number of SB1 systems. So this is my interpretation of this decrease. You can also see here that if we translate instead of effective temperatures, we use the spectral types, how the drop of SB1 system actually occurs at these B2 spectral types. I also have information of the double-line spectroscopic binaries. These objects, we are not able with our methodology to derive the spectroscopic parameters, but I try to make the most fair comparison in a sense that I know that these SB2 systems, or at least the primary component of these SB2 systems, lie somewhere here. And I do observe the same thing, that around B2 type star for the primary, there's the drop in the number. So we have all these empirical results that tells us that, yeah, the end of the main sequence should be located somewhere here. But I have not explained something. So then, which is the nature of the fast rotating stars? So now I'm going to move a bit into the nature of these objects now that I have defined my end of the main sequence. So for massive stars, we know for many years that the distribution of projected rotational velocities follows a bimodal distribution. We have a majority of slowly rotating objects and then a tail of fast rotating objects. If I translate this, again, I translate this into histograms, we have two observables, where we can see the two components, the slowly rotating and the tail of fast rotating object. We notice, we can see better with our sample, that there's a slow decrease with effective temperature. Now, these stars, B-type supergiants, when they evolve more or less at a constant luminosity. So we can say more or less that what we see here is some sort of the evolution of these stars. So we see that, okay, they seem to slowly decrease their rotation. There must be some slow surface breaking effect occurring along the evolution. Also, we see that the number of fast rotating objects is more or less the same. So it could be that once this binary system, these fast rotating objects are formed, they don't spin down. Or if they do very slow. The fact that the majority of them are slowly rotating tells us that maybe massive stars are born with slow to mild initial rotation. And just for the context, over the last 2 decades, many people thought that massive stars are born with very high rotation. But this is not what we see. Our proposed solution, that has been also proposed previously, is that the fast rotating component is likely a product of binary interaction, in which one way or another the stars are spin up during this interaction. Just to put an example, if I transfer mass from one star from the primary to the secondary, and then the primary dies, becomes a black hole, the transferred mass will spin up the secondary, producing what we see here, fast rotation. So we wanted to investigate further. Now we provided this explanation for fast rotating objects. We also wanted to investigate whether we have in our sample stars that are evolving bluewards, like these ones or these ones. As also the possibility that within our sample we have binary products. Now, this is actually the most complex thing that we are facing now within the field of massive stars, to try to find which are those stars that have interacted or that have interacted from a companion or because of a companion. Again, I'm showing this figure from the Mink et al. 2014, in which it is predicted that half of the apparently single stars have interacted with a companion. So for the former group, for stars that have evolved bluewards, theory tells us that we would expect an important chemical enrichment once the stars have evolved after the Hertzsprung phase. We would expect from several episodes of mass loss during the Hertzsprung phase that these stars are rotating slow, and we would expect from this mass loss to have different mass over luminosity ratios. For the binary product, it's a bit more tricky, because this is state of the art. There are some cases in which aside the one that I mentioned before, in which you transfer mass from the primary to the secondary, in which you would expect spin up, but it's also predicted that magnetic fields can spin down the star. So there's a variety of situations. Also, depending on in which moment of the evolution you transfer mass from one star to the other, you may or may not have chemical enrichment in the surface. So the situation is quite complex. Now, to test the first scenario, to try to find stars that have evolved bluer, we were obtaining the spectroscope, or we obtained the spectroscopic masses for our stars, and we were comparing them with the evolutionary masses. We would expect that beta supergiants, since they have lost enough mass in this red supergiant phase, we would expect to see them with lower spectroscopic mass. We would expect to find them somewhere here. What we found was something that wasn't new, but it was never shown with such a large sample, is the mass discrepancy problem. And here I have, again, to go back like 30 years ago. It is a problem that we have not yet solved. We believe it's connected to the way we derive gravities, but we are not 100% sure. But we see that there's a 50% discrepancy between the two masses, but in principle they should be the same. Still, if we adopt, let's say, this difference as a systematic difference, we would still, we would still want to find if these stars involving bluer appear or not here, and we found that they do not. Also, in a preliminary work, we were comparing the pulsational properties of the stars in the sample. Basically, we obtained the periodograms from the light curves of the stars. So with test data, we are able to retrieve this light curve. We turn them into periodograms, and we can see the highest peaks of these periodograms. Now, some predictions that, okay, this is a bit outdated, but just to put an example, predictions by Sayo in 2013 predict that post-red supergiants should pulsate and generate peaks in the periodogram somewhere here. We do not find this. But I just want to show you that asteroseismology is also important in massive stars and will certainly be in the future. So, from our investigations in this regard, we have not found yet any evidence or preliminary evidence of the presence of post-red supergiants. Now, regarding the binary product, now it becomes interesting because we are we're able to combine a lot of information. We have the helium surface abundances that can tell us whether the star has been contaminated or not. We have the spectroscopic evolutionary masses. We have those systems detected at SB1. We have the rotation. So we have a lot of empirical data in a very complex puzzle, and we need to find which stars are likely products of binary interaction. So I'm just going to show you a couple of examples that we found in the last, this is a paper that's still in preparation, but we found two interesting groups of stars. We have this group of stars here. The fact that here it shows again the mass discrepancy problem, but this is not so important now. The important thing is that all the stars that are within this box are helium-rich. And we find this group of stars here that are fast rotating and SB1 systems. We call this, or the way I interpret this, is that probably these stars correspond to case B mass transfer. Case B means that the transfer has not occurred during the main sequence, but when the primary star, the one that has more mass, has evolved, it, for example, became a red supergiant, contaminating the atmosphere, and this contaminated material is transferred to the secondary that suffered spin-up, fast rotating, and then this star that gives the material will explode, will die, and we don't see the companion. And when this massive star dies, either becoming a neutron star or a black hole, we will not see it in the spectrum. So we have all the ingredients. We have signatures of process transfer material, we have fast rotating object, and we have SB1 system. So this was one of the important results of this work. These are likely binary products. Cool. Now I'm going to show something that is, in my opinion, even more interesting. We have such a large sample that what we did is to make in the HR diagram, we made slices of the same luminosity. So as I was saying, I don't have an HR diagram here, but if you remember, stars evolve, or massive stars, at some point evolve at a more or less constant luminosity, which means that all the stars that are within one luminosity beam, they should have more or less the same mass. In any case, along evolution, we would expect to have some mass loss, for example, from, I was showing before that stars lose some mass across the evolution. It's not what predicted by Bing, but still, we would expect that the spectroscopic mass would be the same or lower across the evolution. So if we see that there are stars that are more massive within this luminosity beam, it means that something happened there along the evolution that is not predicted. So doing this in one luminosity beam, we obtain this figure here. So here is the helium surface abundance. I didn't mention, but I consider the way we adopted as helium-enriched object is those stars with a helium surface abundance above 0.3. And in this diagram, I'm also showing the helium surface abundance. And I'm separating the sample within one luminosity beam in two groups. Stars that are before my empirical end of the main sequence, that are colored in blue, and then stars that are located beyond the terminal H main sequence, that are colored in red. Now we see these are the average, the blue dash line and the red dash line, and we can see that for the stars that are after the end of the main sequence, they have higher masses. So how could this be? I mean, in all the cases, it would be less, not more. And we found the reason for this into this group of stars that we find here. So these stars are helium-enriched, have systematically larger masses than their companions within the same luminosity beam, and therefore, they're located beyond the end of the main sequence. So we believe that these stars are, as it is now, the strongest candidates of merger products that we have found in the galaxy. And they are contributing to higher masses because if you have a merger, you are adding the two masses into one object. So the mass suddenly increases, right? Interestingly, we found these objects located or contaminating this top histogram that I was showing at the beginning. That I was saying, okay, here in this top histogram, we don't really see the end, or not that well, we don't see the drop in the number of objects. Well, if this is contaminated by this kind of object, of course, I mean, this is not representative of single star evolution. So this is the way that we are now investigating the possibility, or there's the way we are trying to find now these binary problems. I did one preliminary work on CNO abundances. I selected also a subsample of 50 stars that are located here in the HR diagram. I took stars with very different properties, like fast rotating objects, stars that are single line spectroscopic binary with helium enrichment, and so on. So it's objects of all different kinds. And I also took two objects of those that I showed before, of those that are here. Interestingly, or what evolution says is that, okay, the nitrogen over oxygen and nitrogen over carbon, it will increase, but it would not reach this unless something exceptional occurs. And we believe that this is because these two stars, that again are this one, two of the ones here, have merged. I mean, these are our strongest candidates of merger products. And while the rest maybe have evolved through single evolution, or if they have interacted, they have not received enough mass. I mean, there are many, let's say, many possibilities, but one of the predictions is this one for the mergers, and this is what we do. And I think, yes, I'm gonna give some conclusions because there's a lot of work here. So, conclusions of this work, or my thesis. So we built this high-resolution spectroscopic sample of more than 1,000 O9 and B-type stars that we gathered from the Jacob project. We reached up to 70% completeness up to 2 to 3 kiloparsecs, which ensures us, let's say, reliable interpretations for our results. We performed the line broadening, the spectroscopic, the line broadening analysis, the spectroscopic analysis, and we derived the parameter, the associated parameters for around 709 and B type, or 109 type stars and 650 B type supergiants. Identifying also SB1, SB2, or SB3 systems. We found that the relative number of stars decreases at 2225 kilokelvin, which we believe it marked the end of the main sequence for massive stars with initial masses between 12 to 40 solar masses. Also, we found that fast rotating stars and SB1 systems can also be used to delineate the TAMS, although with some exceptions. Then the properties of the BSGs distribution with against effective temperature suggest that there's an important or efficient angular momentum transport. So at the same time, the stars are not slowing down that fast because the core transfers this angular momentum to the surface. So the stars are slowly decreasing. There's a slow braking effect that I mentioned before. The tail of fast rotating objects more likely are the result of binary interaction. We found this no increase of mass loss rates of the stability region. I didn't mention it, but we are suggesting to the community to urgently change to other models, other predictions for mass loss rates, because this has also implications in stellar evolution in general. And beyond evidencing this mass discrepancy, we do not find presence of post-red supergiants, but we find different groups that are likely the result of binary interaction. Of course, the way to go now would be to extend this analysis to the full sample. That is something that I will do at some point in the near future, hopefully. And this is the presentation I wanted to do. So thank you.
We have now time for questions.
Thank you very much for your presentation. Very clear and thank you very much. One question that perhaps I have to understand properly. Are you assuming that all the stars in the locus of the theoretical main sequence are real main sequence stars? I mean, if I remember well, from courses in stellar evolution, especially when you have an important mass loss, the locus of the helium burning phase is located more or less in the same place at the main sequence. So how can you rule out that a fraction of them cannot be post supergiant range stars?
The thing is, what we are trying, you mean like the stars that are working lower that
I
end up here?
come back for the rest
Yes. Because, I mean, this is what we wanted to investigate here. I mean, this is the main sequence. So if we find these objects, they should be somewhere here, but we don't find them. So, because they have lost enough mass along their evolution, well, in this red supergiant phase, so we would expect to have a different ratio, mass luminosity ratio, but we don't find them. Yeah. So it's what the model predict, and this is actually what we're always saying, like we have to be careful because this is our best approach to finding the terminal main sequence, but we cannot rule out that there is contamination here.
Yeah, that's what I mean.
Exactly. However, from the results, it doesn't seem that, or we don't seem to find these phosphate supergiant objects. So maybe they are not reaching this part here, or maybe they end up somewhere here. But so far, I mean, from these results, we don't see them. So that's actually something that is important constraint for the evolutionary model. Yeah. It seems that it's more towards binary than towards phosphate supergiant.
And also, since the width of the main sequence depends a lot on the overshooting parameter, how are you doing this? I mean, you are choosing an overshooting parameter that fits your observation, or so are you playing with it? Or?
This work that I find particularly interesting, the one by Martinez in 2021, this is exactly what they are trying to do. They are trying to see with the best sample that they had how to play with the different core overshooting parameter to try to reproduce the back then terminal edge of the main sequence. It has been proposed that this core overshooting could be mass dependent, so that depending on the mass, you can extend more or less the width. I, as observational astrophysicist, leave this to the theoreticians to tell me where the end of the main. I mean, it's for them to, let's say, compute models, fine-tune this core overshooting parameter, and try to adjust to the empirical data. But this is exactly, I mean, I know Sebastian, and this is actually one of the things I want to do with him, to try to play with the sample and see how.
But with your data, you're putting constraints on the overshooting parameter.
Exactly.
That's really perfect.
Exactly. This is actually one of the main results of the fourth paper, in which we are actually proposing this to adjust the core overshooting parameter to try to match our end of the main sequence.
Thank you very much for the talk. I have a question about how you made the selection of the stars. You mentioned try to be a volume complete sample, but you take it in some way the age of the star, if there are a star forming region or not, or.
So in principle, what we did, we were launching this large program that we got accepted for the Mercator and the Node. And we use this catalog that includes all these objects that are embedded in this cluster. And of course, the only missing objects, or all those objects that we would miss, are those that are extremely extinguished. So in some regions that maybe there are some newly formed massive stars embedded into this molecular class, we may not see it. But the thing is that we can afford, with the luminosities that we have, we can afford, I think, like 6 or 7 magnitude of extinction, which is a lot. And we believe that the fraction of stars with more than 8 magnitude extinction would be relatively low compared to the ones we have observed. Of course, there are some stars that we may miss, but we don't believe that affording that many magnitude of extinction, they would be too many.
Yeah. But you consider all the stars in the same way, so it's not the age parameter is not taking.
No. Exactly. All those that from this catalog are considered OB-type stars. Actually, we are also trying to be complete in the O-type regime, so we are observing still. I think there are some observing campaigns now that are going to happen in the next years that we already got accepted. Actually, it's a proposal made by Pantaleón y González that aims at observing all the stars that we don't have in the database. So
okay.
The goal is to reach 100.
And also about the rotation, you mentioned that you use ET9 to characterize, but at some moment also mentioned tests to derive rotational periods, I imagine, with the periodograms. So.
But with the periodograms, what we obtain is the frequencies of the pulsation or the variability of the star, but not the rotation.
Yeah, is that
No. But there's also, I mean, I didn't dig that much into the variability from tests because there are enough things that are
another phenomenon.
And also there's the situation that we are not so sure which is the origin of this variability that we observe in the periodograms. It could be waves originated in the surface, in the core, variability. So
and finally, for the termination of parameters that you use NNC methods for with some models, do you use particular feature in the spectra or all the spectra, or how do you?
We have to. This is actually the NCMC working. So this, yes, we have like diagnostic lines. Of course, we have some spectral lines that are more reliable than others, and we have selected those. Of course, you need to select. I mean, if you want to derive the temperature, you need lines that can provide you the temperature through the ionization balance. So here we have helium-2, helium-1 lines, silicon-2, 3, and 4, depending on the temperature. H-alpha for the wind strength parameter, then Balmer lines for the gravity. So yeah, we have like a set of diagnostic lines, and then this has been also part of the thesis to identify which lines provide they are more reliable than others, because not all the atomic models are perfect, the ones we have. So.
And also, when you talk about abundance, it's only for particular elements when you have lines.
Exactly. And actually, yeah, that's the thing, that sometimes we are disabling the CNO, and we're just concentrated in the helium and also the silicon. But then for these CNO abundances, we have to turn them on, and then. But sometimes, yeah, evolutionary. I mean, yeah, atomic models is something that we are sometimes struggling with, because we don't have definitive ones, and of course, this is an important area of improvement. Yeah. Okay.
Any questions on Zoom? Armando?
Thank you. Very impressive and huge amount of work. I have one question that is actually connected to is after the one that Javier was asking. So you can go back to the same plot with the evolutionary masses over the spectroscopic ones, where you have this elliptical region defined.
Yeah.
So you said that in that region you don't see a star, especially in the low temperature region, so you think that means that there's no star going back, evolving bluewards from the supergiant phase. But the thing is that why do you put that region there? Because, as you said, there is a mass discrepancy problem, so it could be that all those that you see below 1, but many of those that are below 1 are the ones that are actually evolving blueward.
Yeah,
why is not the case?
Yeah, I mean, this is something, here there are two things. One, the way we derive the evolutionary masses. This I didn't mention, but we want to improve this, because now we are doing something that is relatively simple, but we want to improve this, so this hopefully will narrow down. And indeed, I'm also hoping that once we improve the way we derive or we obtain the evolutionary masses, to try to see if here I get something. But this I also would expect, for example, I would not expect to find stars rotating fast, but I have some, and so on. So indeed, this is something that I want to investigate further. This was actually something in a paper that is still in preparation, and here's where I'm going to look for them. But this, I mean, requires at first to get better estimates of the evolutionary mass. But yeah, I mean, the thing is that I would expect, if this, I assume, as you said, like this is the mean, let's say, and I should expect to find them here, but it could be that some of them are.
Just to be controversial, why the mean means that they are not evolving bluewards?
Sorry?
Why the mean, I mean, you're saying like the mean will tell me where the normal ones are, the one moving rightward.
No, yeah, we don't see two groups here, let's say. We'll expect to see at least some difference, but we don't find any difference at all. I mean, these two groups, doing some statistical test to see if I find two different populations, we don't find any. So, yeah. I mean, it's a good point. Something that is in the research.
So even if they overlap there, you have other parameters to see whether they are.
Yeah, exactly. Typically, I mean, combining everything, they should rise somehow. Yeah.
Any other questions? Well, if not, I think we can thank Abel again.